Okay, so process XD is just this guy, right? This is an isochoric cooling. Since the piston doesn't move, this is the case where work is 0. Okay, the piston has to move for the process to do work. And if it's just cooling, so basically what's happening here is that Q is equal to delta U plus work. Well, the heat, this is going to be a negative change in internal energy. Therefore, heat's going to flow out. These are both negative in this case. Okay. And really all we have to do is to figure out the number of moles, which I've done before, right? So the number of moles is going to be PV over RT. And we know here the pressure and the volume, and we know the temperature, right? So we know it's 430 there. So if you plug all that in, you get that the number of moles is 0.22388 moles. Okay, using this point right here. Okay, so now we know the number of moles. Let's find the temperature at D. Okay, well, here we can use, I would advocate that you could use the ideal gas law since we know the number of moles, but this is so easy, right? PV over T is equal to PV over T. The volume stays the same, right? The volume for that whole line for XD is 1 times 10 to the minus third, right? So pressure over temperature is pressure over temperature. So 8 E5 over 430, that's here, right? Equals 1 E5, that's the new pressure here, right? Divided by whatever that temperature is at D. And if you see what we're going to do here, we're going to go this times this divided by 8. So it's 1/8 of 430, which you could have figured out just by looking at it, right? 53.75. Okay, so let's see. Find the temperature at D. We just did that. Woohoo! All right, so find the temperature at D, find the work, the delta U. Okay, so let's do delta U. Okay, so delta U is equal to 3/2 NR delta T. So that's going to be 3/2, the moles that we just figured out, 0.22388 times 8.31. And then our change in temperature is final minus initial, so 53.75 minus 430. Let's do it. Okay, so 3 divided by 2 times the moles. There it is. Times 8.31 times left parenthesis 53.75 minus 430. And I get negative 1050, which is a strangely even number for using all this crazy stuff here, right? Okay. And so one might wonder, how else might one calculate that? There's got to be another way, right? Whenever you get like an even number like that, you're missing something. And of course, the shortcut here is that delta U is also 3/2. What is it? It's going to be P, or delta P V. Okay. And the reason we can do this is that remember that PV is nRT, right? Here's nRT. Yeah. So you can plug in PV for nRT. And I think only if one of them changes, though. The other one's got to be constant. So if you have a constant pressure, constant volume, then nR delta T becomes P delta V or delta PV, like this. So in this case, it's the pressure that's dropping, right? So let's do that. Let's go 3/2. Our change in pressure is 1E5 minus 8E5. And our volume is 1E minus 3. Let's try it. Hopefully we won't discover the great flaw in physics, as my high school friend. Okay, so times 1E5 minus 8E5. And these E5s come from this, right? Okay, let's see. Times 1 E minus 3. Well, holy cow, that's also negative 1050. So, life is short, and so is the time you have for the IB test. So go ahead and use this. This is the way to do it, right? So now the question is, let's see, we found the delta U is negative 1050. So let's figure this out, right? We want to figure out the Q. Well, Q is delta U plus work. Now, the piston doesn't move. Remember, work is pressure delta V, okay? Delta V is 0, so there is no work done. So all that's happening here is the heat flows out of this thing. We just cooled it down without changing the... It's sort of like we had a Tupperware, and it was really hot, and we cooled it down to really cold, okay? To 53.5 Kelvin, 75 kelvins. Okay, so if we do this, this is 0, so we get Q equals negative 1050 plus 0. So therefore, Q is negative 1050, which means that 1050 joules flowed out of this gas. So that's why the pressure dropped. Did we answer everything? I think we did.